So here's F, Michael. So just like I wrote R as an expectation over the set of rewards that you're going to see after K steps, I'm going to write F in the same way. And I've sort of got some really funky notation here, but let me try to explain it. In English, F is simply the expectation of me ending up in S prime after K steps. So this delta is because I can't draw lowercase delta as well. This is a delta function. It is 1 in the case where the kth state that I see is actually equal to S prime and 0 otherwise. And delta to the K is just, well, the discount factor raised to the kth power. So F is an expectation over, after I've executed the option, that I will end up in state S prime, having started in state S and having taken K steps. Now, notice, why do I even have to go through all this? Why couldn't I just put T of S, comma O, comma S prime here? Well, first off, T is defined in terms of A. It's not defined in terms of O, but that's okay. The reason I have to do this little funky thing and why we call it F instead of T is because, as you pointed out in the beginning, there needs to be a discount factor attached to the value of the next state, which in this case is S prime. So what we've done is we've rolled up that discount factor inside of F. So F is the expectation of me starting in S, taking option O, ending up in S prime after K steps, and the delta sub K gets sort of brought along with that expectation so that I can appropriately discount the S prime state that I will end up in.
Okay.
Right. So in the end, both R and F are just expectations. They're exactly doing what they were doing in the original Bellman operator, Bellman equation that we're using before. In the original Bellman equation, the reward was just the immediate reward that we got for taking an action. Here, the reward is just an expectation over all the rewards that we're going to see given that we've taken this particular option. If the option is, in fact, a single action, then it would be exactly the same thing as the reward we would get for being in that state and taking that action. Similarly, F is just a transition function, except now it's sort of the accumulation of all the transitions of starting at S and ending up in S prime after K steps, given that I took the particular actions that are inside of the option and defined by pi. Now, there's a couple neat facts about this, and I will write them down on the next slide, but I just want to point out what's particularly cool about this is that it really is a Bellman equation. It really does allow us to do all of the things that the Bellman equation, Bellman operator allowed us to do in MDPs. But it allows us to analyze or to reason about or to plan over this multiple variable time MDP. So in fact, this kind of MDP has a name, which I probably should have written down earlier, and it's called SMDP, where the S stands for, what do you think, Michael?
Something?
Yes, and that something is semi. So this is called a semi-Markov decision process, and the difference between the Markov decision process and the semi-Markov decision process is you get to make these jumps in time. And because we have this Bellman operator that takes into account all the possible jumps in time that you might take, in the end, it grounds out to an underlying MDP and allows us to inherit all the things that Bellman allowed us to inherit.